Okay, so before we start, to give everyone a glimpse of the amphitheater experience and what frontiers in physics would look like usually in offline mode, we have prepared a short video for you all to see.
Okay, so let me share my screen and start that video. What's the issue here? Okay. Can you hear now? Yeah. Sorry? Yeah, okay.
All right, so now we will have a lecture by Professor Dhruba Saikia, and I would like to ask my friend Pranav Limay to introduce him.
Thank you, Adishri. So, good morning, everyone. Today we have Professor Dhruba Saikia with us to give a talk in the 14th installment of Frontiers in Physics. So, a little bit about him. So, Professor Dhruba Saikia is currently leading the Teaching and Learning Center as well as the National Resources Center of IUCAA. He has a lot of experience in doing research and has immense interest in teaching others. So, he was a professor at National Center for Radio Astronomy of the Tata Institute of Fundamental Research for over 40 years. He is also the founding vice chancellor of the Cotton University in Guwahati, India. Apart from being associated with these Indian institutes, Professor Saikia is also associated with overseas institutes like the Jodrell Bank Observatory of the University of Manchester, the National Radio Astronomical Observatory of US, the Queen's University of Kingston, Canada, the Australian Telescope National Facility of the CSIRO, the University of Western Australia. So, Professor Saikia has specific research interest in the field of extragalactic astronomy and astrophysics, mainly focused on the study of active galaxies, and has published over 150 research papers in leading journals. He is also awarded with the Professor M.K. Vainubapu Gold Medal of the Astronomical Society of India and is a Fellow of National Academy of Sciences, India. Sir, we are very grateful to have such an eminent personality like you to give us a talk entitled Extracting Energy from Gravity to us. Over to you, Professor Saikia.
Thank you very much for the kind invitation. Let me first just share my slides and then I will start off. Sorry, 1 second. Okay. Is it all right, Pranav?
Yeah, absolutely.
Okay, thank you very much, Pranav, for the very generous introduction. And to all of you, including Dr. Davadi, for the kind introduction, for the kind invitation to speak on this occasion. As most of the students are likely to be undergraduate students, I thought I would keep it relatively simple and also touch on astronomical implications of extracting energy from gravity. Okay, first, always starts with a picture of a bird. It is not really a talk on birds. And what this picture shows you is a picture of a bearded vulture, also known as lammergeiers, and whose diet consists entirely of bone, about 70 to 90% of it. And it can swallow bones about 30 centimeters in length, which are digested by hydrochloric acid in its stomach. And this is one of the few vertebrates, I think perhaps the only one, whose diet consists entirely or almost largely of bones. But these birds have learned to use gravity to break down the bones or big bones into smaller pieces. And what they would do is that they would soar high into the sky and drop the bones onto hard rock. And this was quite amazing, actually, to find that birds have actually found a way of using physics that we know to sort of process their food in a way that makes it more easy for them to process it. And vultures are not the only one. In fact, Julian Huxley, I think it was a zoologist who, in Tanzania, naturalist zoologist, who found a lava track which was just full of bones, and these were possibly dropped by birds from a height to try and break them into smaller pieces. There are other species as well. For example, there were reports by Pliny the Elder, who lived in the 1st century, Common Era, author, naturalist, and who was an army and naval commander of the early Roman Empire. And his book called Naturalis Historia was one of the seminal books till the Middle Ages in natural history. And he wrote about an eagle that would drop tortoises from a height to crack open the shells. And this was actually not really believed for many years. And it was only in the 1980s, I think early 80s, that zoologists observed golden eagles and soaring high into the sky, 60 meters or so, and dropping them to smash open their shells. And they noted that sometimes it wouldn't crack open at one dropping, they would have to drop it multiple times. And I think the largest number of drops that was required was 8 or so, from what I recollect from my readings. So you can see that different species of birds have used, I've just used the example of birds, use the force of gravity to try and get at their food. And one of the very sort of cute little videos which you can watch, I put the link over here. If you Google Attenborough and crows and intelligence, you will get this as well, that they were known to drop nuts from a height to get to the kernel of the seeds that of what they were eating. And then they found that some nuts were too hard to crack. And this was done in a city in Japan. And they would drop it and let the cars crush it. But of course, there was a problem because traffic was there, so they would not be able to access the food easily after the cars had crushed it. So they later learned to drop it at the zebra crossings. And there people are very, sort of disciplined in terms of crossing the road when the lights allow them to cross and cars stop. So the crows learned to drop the seeds in the zebra crossings, and the cows would crush it and they would actually go and get at their food while the traffic was stopped. So you can see there's a fair degree of intelligence, but without doing any course in physics, these different species of birds have learned to use gravity to get at their food. So what really happens, as students of physics, you would know that suppose a particle is dropped from infinity, say with zero potential energy, zero kinetic energy, that it'll build up its speed as it approaches a body of mass m, and then it'll get more and more strongly bound to that body. So the gravitational potential energy gets more and more negative, and the kinetic energy will keep increasing. But the kinetic energy will keep increasing. Of course, one has to be, one had an atmosphere, one will also have to deal with terminal velocities, but it cannot go on infinitely, because at some point it's going to hit a surface. If it's a solid body like the Earth or the Moon or any solid body, all right? And then it's going to stop. So what happens to the kinetic energy? It can go into breaking the bone, as the birds learned. It can grow, and then if it's a single particle like a proton or plasma, it can it'll radiate itself. It can go into heat, which will be radiated away, or it can go into internal energy of the system. So you can see that gravity is being used or can be used in a variety of situations. So today what we look at is a very simplified version of this, And we'll see that how even the most luminous objects that we see can be understood by this basic process of using power from gravity. So I will give a very simplified description without going into great details of more complex processes which depend on the electrodynamics and magnetic fields, etc. But I will just deal with a very simplified treatment using basic physics that you would have done either in the first or second year, first year of undergraduate, or even at a higher secondary level. So my objective was to try and get that message across to you that there's a lot of interesting things that one can learn even using basic physics. And it is always useful to do what we call the back of the envelope calculations to see that the basic processes can explain a rich variety of phenomena in our universe. Obviously, to get into greater detail, one will have to look into the more detailed physics of it, the microphysics of it, etc. But at least to get a broad physical picture of it, a very simplified treatment is often enough. And it also gives you values in the right ballpark. So just as I said, we'll consider matter falling onto an object of mass m and radius r from infinity. And as I said, matter falling from infinity acquires kinetic energy as its potential energy becomes more negative. Now I've considered a proton of mass mp falling from infinity, and just by conservation of energy, you can get half mp. This is the kinetic energy, this is the potential energy. And suppose it hits the hard surface, suppose it's the Earth. At r equal to r, there is a rapid deceleration, and the kinetic energy of free fall is radiated away as heat. Okay. Now, if the kinetic energy is radiated away as heat, we can go and calculate by the rate at which mass is falling. We can calculate what the luminosity of that object on which matter is falling from infinity could be. So I will write down L is equal to half dm dt is the rate at which mass is acquiring, and v free fall squared. I can substitute for v free fall squared by from here with 2 gm by r. The hard radius is r, and then I can get this expression gm dm dt r. So the luminosity is dependent on the rate at which matter is falling onto the compact object. In the context of black holes, it was first put into place what is known as the Schwarzschild radius of any body, which is given by 2 gm upon c squared. In the case of a black hole, or stationary black hole, the Schwarzschild radius is the event horizon, and matter or radiation within the event horizon will not escape the object. So often in literature, you'll find expressions like this, which are expressed in terms of the Schwarzschild radius. So I've just introduced the term, and you can see that greater the mass of the object, greater the Schwarzschild radius of the object. Now, in the case of, you can calculate the Schwarzschild radius for any object. You can calculate it for the Earth, you can calculate for the Moon, you can calculate it for a star. And usually what happens is that the Schwarzschild radius is not relevant for most objects, because the Schwarzschild radius, if you calculate, for example, the sun, it's a mere 3 kilometers or so. And that is much smaller than what we know to be the physical radius of the sun. I've just written down a few values over here. If you want to know more values, you can go and calculate it, or you can Google it, whichever route you prefer. Now, it's usual to do these small sums to just get a feeling for the numbers. Now, if I take Jupiter, it is 2.2 kilometers, much smaller than the sun, 2.2 meters. And you can again see that these are values which are much smaller than the physical radius. The Earth is just about 8.7 millimeters. And again, it is much smaller than the physical radius of the Earth. So in most situations, it does not really sort of play a role. The Schwarzschild radius is much, much smaller than the physical size of the object. But when we come to black holes, it's a different matter, because a black hole is a singularity characterized by charge, mass, and angular momentum. And there, if you calculate the Schwarzschild radius of a black hole, As we saw, it depends on the mass of the object. So greater the mass of the object, greater the Schwarzschild radius of the object. So although astronomically for distant objects, it is very difficult to even resolve the Schwarzschild radius of an object, but we will see consequences of it, and we will try and understand a little bit about it. Now, this is just the supermassive ones that I've written over here, because that's where the Schwarzschild radius will be larger. 1 AU is the average distance between the Sun and the Earth. Now, the luminosity is, as we saw, if we express it in terms of the Schwarzschild radius, it's half dm dt, rate at which mass is being acquired, and the ratio of the Schwarzschild radius to the physical radius of the object. So that is what we had derived just a little while ago. Now, you can ask yourself a question that how efficient is this process? Can I compare it? Suppose I want to generate luminosity. Suppose I want to understand how luminous an object is and what is the process responsible for it. For example, we know that stars shine because of nuclear reactions occurring in the center of the system. The Earth is in thermal equilibrium now. It is much hotter at the center. It receives its energy from the sun, and the atmosphere actually acts as some kind of a cloud around it, greenhouse kind of effect, which we have, and we have a temperature which is reasonably well moderated. Now the thing is that suppose I want to understand the luminosity of an object, I first want to know how efficient is this process, how efficient birds could crack bones with it. But suppose I want to know, understand the luminosity of an object, and I want to see if matter falling onto it. And we'll see under what situations matter falls into it as well. Then we want to know how efficient the process is. Now you can see that I can write this expression down as L is equal to xi dm dt, rate at which mass is falling. And this is just the Einstein's expression of E equal to mc squared, except that because it is the luminosity rate at which matter is falling in, so I've got a factor of dm dt over here. And this other factor, half Rg upon R, I would use it as a measure of efficiency of conversion of accreted matter into heat. Okay. Now you can see over here that if you look at the expression for xi, that if R is going to be large, then your efficiency is going to be low. Okay. And similarly, Rg depends on the mass of the object. So the more massive the object is, the higher the efficiency would be, but it goes along with the radius. I've taken just two examples of stars over here. One is called a white dwarf star, which is a kind of star which our sun will end up as a low mass star like our sun, about a solar mass or so. When it burns up all its fuel, it'll end up as a white dwarf, and it's about a solar mass, and it has a radius of about 5 × 10⁶ meters or so. This is a canonical number. There would be some variations in both the mass and the radii. Then you'll get an efficiency of half Rg upon R of 3 × 10⁻⁻⁴. But as I said, that if you can make it more compact, then you would get a higher efficiency. And also if you make it more massive, you'll get a higher efficiency. So if I take another end product of stellar evolution, which is a neutron star, stars much more massive than our sun, say about 8 to 10 solar masses or so, would end its lifetime as a neutron star. There would be an explosion, a supernova explosion, which will leave behind a remnant, which is a neutron star. Okay. Now here again, the mass is, I've taken of the order of a solar mass or so. It could be slightly heavier than that as well. And this is again a canonical number, 10 to 15 kilometers. And you can see that half Rg upon R is about 0.1. So once you go to a more compact radius, your efficiency goes up. So accretion or infalling of matter onto a neutron star could be a very efficient or powerful source of energy. Now, suppose I say, we mentioned a little while earlier that energy is generated in the interior of stars via nuclear reactions. In a star like our sun, the energy is generated largely by a chain called a proton-proton chain, which is, and the efficiency of that is about 7 into 10 to the power of -3. So you can see straight away that this is a process that by matter falling onto an object, a compact object, a massive compact object, you can generate energy more efficiently or get energy more efficiently by matter falling onto a compact object due to gravity than what you can get even by nuclear reactions occurring in the center of the sun. And heavier stars will have different processes going on. For example, Sirius, the bright star which you can see in the sky, which is only about 2 times more massive than the sun. But because it is 2 times more massive, its central temperatures are higher, and it goes via, most of the energy is generated via what is known as a carbon-nitrogen-oxygen cycle, which has a much stronger energy dependence than the proton-proton cycle. Okay, this is just an illustration of the proton-proton cycle. So effectively what you're doing, you can look at this up later, so I won't spend too much time on it. But basically what you're having is proton nuclei fusing to form deuterium, combining with another proton to form a helium nucleus, and 3 helium nuclei forming a 4 helium nucleus over here. This is the main source of energy. There are other branches possible as well, but this is the main process which generates most of the energy. So what you're effectively having is you're combining 4 protons to form a helium nucleus. You start off with 3, but you give up 2, and then there's positrons and neutrinos and energy emitted as well. So this has this whole process which sustains life on Earth, which is responsible for the temperatures of our planetary system, and is a process which is far less efficient by a factor of 10 roughly compared to what you can get by matter falling onto a compact object like a neutron star, which is about the mass of a sun, but about only 10 to 15 kilometers in radius, which means about Ferguson College to Swargate or slightly beyond that. So it is, you can see how compact the object is, and it is because of that that gravity plays an important role. So I just wrote down over here, 4 protons combine to form a helium nucleus, and the difference in mass is about 0.029 mH. So efficiency comes out to be about 7 into 10 to the power of -3. Now, the question to ask oneself is, could we do even better if matter is accreted onto a black hole? So there we come into a slightly different domain. I will only delve on it at a slightly superficial level or very simplistic level, and without getting into too many complications. Now let us look at what happens into a black hole. Now suppose matter is falling radially onto a black hole. Okay, if matter is falling radially onto a black hole, it will go beyond the event horizon and it will be lost forever. So there is not much that we can get out of it if matter is falling onto, say right now I'm considering a Swatchshell black hole, which is a non-rotating black hole, and we'll not be able to get into it. But what saves us, or what enables us to get energy out of it, is that matter, when it falls onto a compact object, usually or almost invariably, that infalling matter will have some angular momentum. Okay, so as the angular momentum, because it has angular momentum, is rotating, when it goes closer and closer to the black hole, it's going to rotate faster, and matter can fall into the black hole. But before that, what happens is that the rotating matter will actually collapse in a direction which is orthogonal to the direction of rotation, whereas orthogonal to the axis of rotation, you will find that centrifugal forces will actually prevent it from falling radially inwards. And But to actually get closer and closer, the matter will also have to lose angular momentum. And this is achieved by the viscous forces in the disk itself, because matter will have viscosity. It will be a turbulent disk as well. And this viscosity redistributes the angular momentum so that some matter goes outwards and some matter falls inwards. This particular sketch is actually a simulation which was done by the NASA Goddard Space Flight Center. And I've just given the link over here. I can share the slides or a PDF file with you later. But this actually is a series. I've just taken one slide from it, but it actually gives you what the black hole would look like in terms of the recent image of the black hole of M87, which has been imaged by the Event Horizon Telescope. And you can imagine that, very close to the black hole, light will be bent by large amounts. And you can see the back of the black hole as well while looking at it close along the edge over here. This is just a face-on view of it. And it will be interactive to just look at the simulations, because there's a lot of physics which is built into it. And also because the matter is rotating very fast, when you're looking at it edgeways, that some of it will be Doppler enhanced due to relativistic beaming, and once going away would be Doppler diminished. But we'll not get into the complexities of the disk itself. But all I want you to know at this phase is that matter is accreting onto a compact object, which will form an accretion disk around a black hole. Viscosity redistributes the angular momentum so that some of the material flows inwards and some outwards. And viscosity also acts as a frictional force, which results in the dissipation of heat. Now, what you see over here is that when you look at a Schwarzschild black hole, the efficiency, I've not gone into calculations of that because it's a bit more involved. It's about 0.06, okay, which is again far more efficient than that of nuclear reactions. And if you have a rotating Kerr black hole, Kerr was the one who first derived the general relativity solutions of the rotating black hole. And for a rotating Kerr black hole, it extracts energy from the rotation of the black hole as well. And the maximally rotating black hole, the maximum efficiency that you can get out of it is a staggering 0.426. So you can see that by gravity itself, that you can extract energy which has a far greater efficiency than what is generated by nuclear processes in the interior of our sun. I've taken that as a benchmark today because the sun is itself responsible for our seasons, and we're all familiar with how much energy the sun gives out. We are also moving slowly into more renewable and environmental friendly sources of energy, and solar energy being one of the important components of it. Now, the next question to ask oneself, that having established that, okay, I can get so much of, with a reasonably high degree of efficiency, I can get energy out of accretion onto a black hole. Then the next question to ask oneself is that, how much luminosity can I get out of it? For example, if I have this luminosity factor over here, I have a factor Xi, which I have shown to be much greater than that of nuclear reactions. But if I keep increasing dm dt, can I keep getting higher and higher luminosities? How high can we go? So that is the question that we will try to address in the next 5 or 10 minutes or so. All right. Now, can we go? Now, if any of you want to put a suggestion in the chat box or something, you're most welcome to do so. Or if you want to raise your hand and give you an answer, that's also you're welcome to do so. Okay.
So, sir, can we take the questions at the end of the talk?
Okay, we can do that as well. Okay, fine. Okay, so now let's try and understand. Can we increase dm dt indefinitely so that we can get arbitrary large amounts of luminosity out of it, right? Now, the answer is no. Why is it no? It is no because you know that once energy is being generated, the radiation will also have a force acting on the matter which is falling into it. Okay, so if the luminosity becomes above a critical value, then the radiation pressure or the energy radiation pressure will also start inhibiting the infall of material. So this was an issue which was addressed by Arthur Eddington, and the luminosity that we can get is known by his name, Eddington luminosity. So the luminosity is too great, as I said, radiation pressure can blow away the infalling material. This also plays a role in how massive a star can we have, because if it is highly luminous, then again this radiation pressure will act on the material to blow the outer layers of the star apart. Now, so the most massive stars that we know of today are of the order of, in the ballpark of 200 solar masses or so. And so now we look at a very simple derivation, again, using physics that you would have done in your first or second year of your undergraduate studies. So I've confined myself to try and look at things today where simple physics you would have done at a younger level. So what we got to do is to balance the inward force of gravity with the outward pressure of radiation, outward force of radiation. Pressure is nothing but force per unit area. And when usually matter is fully ionized, falling onto these objects, and so pressure is provided via Thomson scattering. So what we'll do now is consider the forces on an electron-proton pair, which is falling onto the object, okay? And let's see what happens to it, okay? So consider the forces of electron-proton pair at a distance r. So the inward force of gravity is nothing but gmm upon r squared, you know very well, because the electron mass is so much smaller than the proton mass that we have written this down as gmmp upon r squared. So the radiation pressure acts on the electron, but plasma is overall neutral. You can't build up large-scale electric fields over there by charge separation. So pressure communicated to the protons by electrostatic forces between the proton and electron. And the maximum separation is roughly given by the Debye wave. So now what happens is that each photon gives up a momentum. So the photons, have zero mass, but because of Einstein's special theory of relativity, you know that photons have a momentum, which is given by h nu by c, and it gives up a momentum, each photon, each collision with an electron. So the force acting on the electron is a momentum communicated to it per second. And that will depend on the flux density of the incident photons and photons over here, okay? And the number of photons will depend on the luminosity of the object. Higher the luminosity object, the greater would be the number of photons. Lower the luminosity, the smaller the number of photons. So what I've considered over here is the forces on an electron-proton pair at distance r. Gravity is trying to pull it inwards and radiation is trying to push it outwards. And we saw that each photon gives up a momentum h nu by c, so that the force is given by the Thomson scattering cross-section over here, the number of photons, which is would depend on the luminosity of the object. Number of photons, the luminosity would get diluted by 4 pi r squared, and to get the number, I divide by h nu. And you see L is the luminosity of the source, so substituting for n photon and h nu, I would get an expression for the force due to the radiation. And here also you can see that it inversely varies as the square of the radius, as does the force due to gravity. So if I equate these two, the inward force of gravity, which is gmmp upon r squared, and the radiation force, sigma TL upon 4 pi r squared c, I will get an expression for the maximum luminosity that I can get by equating the gravitational and radiative force of the object. So by simple physics, actually, by just looking at the force due to radiation, which is exerted by Thomson scattering. And again, you know that the Thomson scattering cross-section inversely on mass, so it is much greater for that of an electron compared to a proton. And you can see over here that I have an expression for the luminosity, the maximum luminosity that I can get. If the luminosity exceeds that value, then the radiation pressure wins. And if it is less than the value, then gravity wins and matter is going to keep on accreting. Now, the interesting thing to note about this object is that it just depends on the mass of the object. You can see that these are all natural constants: the gravitational constant, the Thomson scattering cross-section, the mass of the proton, and the velocity of light. Okay, so the higher the mass of the object, the higher the luminosity that you can get out of it. So you can see how important gravity is in terms of trying to understand processes that are going on in our universe. Okay, now if I go and put in numbers over there, because I know the values for these fundamental constants, then I will get a number which is this is m is usually expressed in terms of the mass of the sun. Okay, a few times 10 to the power of 30 kilograms. So 1.3 into 10 to the power of 38 m upon m sun ergs per second. And if you'd like to use the MKS units in terms of watts, this will go down by a factor of 7. And here also it is expressed in terms of the Swatchshell radius over here. Okay, but you can see that the greater the mass of an object, the greater the luminosity that I can get out of it. And you know the luminosity of the sun. But on the other hand, if I have objects which are much more massive than the sun, I can get luminosities which are much more luminous than that of the sun. Okay, and okay, you can see over here straight away that that even for one solar mass, you can generate 1.3 into 10 to the power of 38 ergs per second. So you can see it's a very efficient way of generating large luminosities by the accretion of matter onto a black hole. Now you can ask yourself, is like in all sciences, one has to balance it up and see if it's consistent with observations. Now I've written down the expressions over here, I repeated them over here, and RG is the Swatchshell radius, and this is expressed in terms of the Swatchshell radius. Now these are binary systems in our galaxy. Don't worry too much about the differences between low mass X-ray binaries and high mass X-ray binaries. As you know that most stars are not single stars, but in binaries are multiple systems. And here is a schematic illustration of such a system. And you can see over here that matter is overflowing from a donor star to a compact object and forming an accretion disk around it. We haven't spoken about jets today. I didn't want to bring in too many ideas in the same talk. But basically, the difference between high mass and low mass X-ray binaries is the mass of the donor star, right? But you can see over here that the kind of luminosities that one gets, 10 in ergs per second, it's a few times 10 to the power of 38. So if you had a compact star, which is a few times the solar mass of the star, accretion from a compact object, accretion from a companion star can actually produce the kind of luminosities that we see. So you can see that gravity itself, we started with a simple example of birds trying to break bones, right from birds trying to break bones or tortoises, shells of tortoises to get at the food, to understanding the most luminous kind of objects in the universe, that gravity plays an important role. Now you can ask yourself that, okay, can we get, what about the LE for supermassive black holes? So you can see over here that if I put about 10 to the power of 8 solar masses, which is not atypical, the black hole in the center of our own galaxy is about 10 to the power of 6, a few times that. So 10 to the power of 8 is somewhere in the middle of the range. You have black hole masses of the order of 10 to the power of 9 to 10 to the power of 10 or so. you can see that the amount of energy that you can generate is about 10 to the power of 10 to the power of 8 would be 10 to the power of 46 ergs per second. Millions of times larger than the luminosity of our sun. Now we can also ask ourselves, what is the temperature of this object? How hot is it going to be? And there again, we take recourse to physics that we know, because this is a body which radiates roughly like a black body. And so we can go back and think of Boltzmann law. Okay, 4 pi r squared sigma T to the power of 4. And I can put that equal to the Eddington luminosity, which we just derived. So you can see that in the case of, from this expression itself, you can see that when r is small, you will get a higher temperature. And also, if you just look at this structure, which we have not done today and which we will not do today, that a body in hydrostatic equilibrium, it's the ones which are at the bottom will have a higher temperature to balance the pressure above it. And that is why the sun is much more luminous, 15 million degrees or so at the center compared to the surface temperature of about 6,000 degrees Kelvin or so. So the hottest and brightest material near the innermost orbit, okay, innermost areas. And suppose I take a solar mass neutron star, and I take the radius of the neutron star at about 10 kilometers, and I plug in these values of the Stefan Boltzmann constant. I plug in the radius of the neutron star, and I know the Eddington luminosity for the mass. Okay, I get temperatures of the order of 10 to the power of 7 K. All right. Now, the white dwarf stars, which our sun would end up as, would radii about 1,000 times larger or so. Then you get temperatures of the order of 10 to the power of 5 Kelvin or so, right? So now again, you can go back to your physics and say, where will this object emit radiation? Now you can think of the Wien's displacement law. So when you think of the Wien's displacement law, temperatures of the order of 10 to the power of 7 K would be in the X-ray region of the spectrum. And when we have temperatures of the order of 10 to the power of 5K, it will be close to the ultraviolet region of the spectrum. The sun at about 6,000 degrees Kelvin, you know, is in the optical region of the spectrum. So this is just an application of Wien's displacement law, trying to establish temperatures from the peak in the black body spectrum. All right. And the earlier figure that I showed you is the accretion disk and the low mass X-ray binaries and the high mass X-ray binaries. That is because the material falling over here heats up gas to high temperatures, and we get radiation in the X-ray region of the spectrum. All right. And so this is also the temperature that you see, okay, is consistent with the scenario that we have built up based on gravity playing an important role in generating the energy that we see. All right. Now we can ask ourselves the same question as to what about a black hole? Right. We saw that a black hole is far more compact, and here the hottest and brightest material would be near the innermost stable orbit. Okay. Now here there is an interesting factor which comes into play, that the radius we don't have. The black hole is not a solid body like the white dwarf or a neutron star or the Earth, but it is a singularity, and we saw earlier that material within the Schwarzschild radius is the event horizon, within which neither particles nor material can escape. But the innermost stable orbit is about 3 times the Schwarzschild radius. So let us say that material gets close to the black hole, close to the inner stable orbit, and we will try and see what the temperature of the object should be. Again, mass is usually expressed in terms of solar mass units. Now here, there's an interesting factor at play as well, because you see that greater the mass of an object, okay, greater the mass of an object, we saw that greater is the Eddington luminosity over here, all right? But you find that the last stable orbit also keeps increasing as you keep increasing the mass of the object. The Swatchshell radius keeps increasing, and so the last stable orbit is about 3 times that. So matter cannot get, when you get to more massive black holes, the material which is falling onto and which is generating luminosity due to the effect of gravity cannot get closer. It actually, the last stable orbit is further and further away. So if you plot that over here, plug that into this equation, you will get an expression for temperature, which actually varies inversely as the mass, because this is m upon m sun, and then you'll find that R also expressed in terms of m upon m sun will become m upon m sun squared. So m upon m sun is going to go in the denominator over here. So if you plug in the numbers, this is the kind of expression you will get, and T is 1/4 power of this. So when you talk about a 10 to the power of 8 solar mass black hole, which is not atypical, then because of this inverse dependence, okay, you can see 10 to the power of 8 and 1/4 of that will give you 10 to the power of 2, and 10 to the power of 7 minus 2 will give you 10 to the power of 5. And when you have temperatures of the order of 10 to the power of 5, it will be approaching the ultraviolet region of the spectrum. So in one classes of very luminous nuclei called quasars, if you look at the detailed spectral composition, I will not get into other details over here in today's deliberations, but you can see that there is a bump over here, which is believed to be due to this disk over here, which is where the temperatures are of the order of 2 into 10 to the power of 5K. This is an average value. There would obviously be stratification within the disk itself. It will not be uniform across. It will be larger, closer to the inner stable orbit than further away. So this actually just blows up the same figure. So you have a continuum spectrum over here. We'll not worry about the other parts today, but we'll just look at what is referred to as a big blue bump. So you can see the simple ideas of gravity and simple calculations using basic physics that you're all familiar with, that we can try to understand some of the most exotic objects which inhabit our universe. So when I talk about the exotic objects inhabiting our universe, or let me just, I will not go into every type over here, but I will just illustrate to you that the universe is very rich, and our galaxy, for example, the Milky Way, or our nearest neighbor, the Andromeda Nebulae, are what we call just normal galaxies. Our galaxy also has a supermassive black hole in the center of the nucleus, and there is mild activity due to it. But in most of the what we call the zoo of active galaxies, the luminosities in the nuclear regions far surpasses those that occur in our own center of our own Milky Way. So the Milky Way or the Andromeda Nebula are what we call normal galaxies. But we can see that we have galaxies which are orders and orders of magnitude more luminous than that of an ordinary galaxy like the Andromeda Nebula or our own galaxy. And often, for example, in the quasars or the BL-like type objects, all the luminosity or almost all the luminosity comes from a point-like source in the nucleus of the galaxy. And the way we have approached it today, that we saw that if you had a 10 to the power of 8 solar mass black hole radiating at the Eddington luminosity, then you could get an energy which is about 10 to the power of 46 Earths per second. So gravity plays a very important role in trying to understand not only the motions of objects, you're all familiar with Kepler's laws of planetary motion, the dynamics of galaxies, but also the energy generation in galaxies. It is not all stars. Stars play an important role, but you can see there are other processes which also play a very important role. So I will just give you briefly some of the characteristics of active galactic nuclei, and then I will discuss a little bit more about active galactic nuclei for 5 or 10 minutes, and then with some closing remarks on the way this field has developed, I will leave the floor open for questions. So what are the characteristics of an active galactic nucleus? Remember that this is right in the nuclear region of a galaxy, okay? Usually unresolved from ground-based observations. When I say usually, traditionally it has been about half an arc second or so. With radio VLBI, it has been better. And with telescopes outside, like the Hubble Space Telescope, it's about 50 milliarc seconds or so. But the nuclei, we are still far from actually being able to resolve the Swatchshell radius or the last stable orbit in almost all galaxies. So they characterized by high energy output from the nuclei of galaxies, often more luminous than an entire galaxy. You have jets of plasma squirting out from the nucleus at velocities which could be close to that of light. You have very prominent emission lines. Now, emission lines are due to gaseous material which is moving about. If you take the spectrum of a galaxy like our Milky Way, like the Andromeda Nebula, which is a normal galaxy, they are actually by and large the sum of the spectra of the stars. And stars have absorption lines, are characterized by absorption lines by and large, and that is because of absorption by the cooler outer layers of the photosphere of the radiation coming from below it. But typical line widths are never so large for the absorption lines, and even for the emission lines, it is not very large. These prominent emission lines arise in the nuclear regions of galaxies, and when they have velocities of thousands of kilometers per second, it implies that their motion is governed by a very massive object. And one can use that information as well to estimate what the mass of the supermassive black hole at the nucleus could be. And these nuclear regions are often variable. You can see that our sun varies a little bit with the sunspots, but its variability in the optical is very small. It varies far more dramatically at the radio, but the energy output is largely in the optical region of the spectrum and from the sun itself. But these sources can vary by several factors in very small time scales of hours to days, just to give you some typical numbers. So they're strongly variable. So you can see that there's a wide variety of phenomena, and we need to understand these aspects, incorporating the energy source, which is gravitational in origin. This is just a picture of the Andromeda Nebulae, and a little bit which is blown up over here is that Andromeda has such a large angular size because it is so close by that the HST has to take multiple shots and build up a mosaic of it. And this is the panchromatic Hubble Andromeda Treasury program, which shows a part of the galaxy over here. So this is what I mentioned about being a normal galaxy. But if I were to go into galaxies which are active and a lot more energy is being generated, there is one class which are called starburst galaxies. That means there is an intense burst of star formation taking place. There are a lot of massive stars which explode in a relatively short period of time, almost like crackers going off in Diwali time, focused at a particular period in the history or lifetime of a galaxy. Normally, stars are born and stars are dying. A normal galaxy like the Andromeda Nebula or our Milky Way, the passive evolution of stars keeps happening all the time. New stars are born and old stars die. The more massive stars die much more faster than the lower mass stars. But in the case of these galaxies, for example, the star formation rate is much higher. For example, in our galaxy, it's about a solar mass of that ballpark per year is the average star formation rate. Here, it could be orders of magnitude larger in the more extreme cases of starburst galaxies. So this was characterized as an exploding galaxy And Philip Morrison gave a talk on it many, many years ago, a very inspiring talk on it. Today, of course, we have a lot more information on it, and we know that this intense burst of star formation creates a hot bubble with matter escaping along the minor axis of the galaxy, carrying the different components of the interstellar medium, which is a matter between galaxies along with it. This is again another image of an antenna pair of galaxies. These are galaxies in collision. I'll just show you one or two pictures to illustrate to you the diversity of phenomena in our universe. And when this happens, gas gets compressed, there could be new stars which form. And when you Google up, interacting galaxies, you'll find many, many more exciting images, which we try to understand in terms of the physics that's going on. So as I mentioned earlier, for starburst galaxies, more than 100 solar masses of per year could be the star formation rate. And in fact, when stars are born too, gravity plays a role, because gravity has to overcome the internal forces. For example, you know that the pressure is related to the temperature, pressure directly proportional if it is an ideal gas. And if the cloud is too hot, then it's not going to collapse. If the cloud is, it has to be a cold cloud, and gravity has to be strong enough to make it collapse. So gravity plays a role not only in generating energy from binary systems, from the nuclear regions of galaxies, but also in the very process by which stars form. So I thought I would just mention it without going into details on that, because to fit it into the timescape. But the kind of galaxies that we talked about with a supermassive black hole in the center, and matter energy being generated by a process of accretion, are what are called these most active, most luminous of galaxies, radio galaxies and quasars, which were discovered when the universe was opened up outside the optical region of the electromagnetic spectrum, and the radio window opened up in the early 30s. And today, of course, we observe all across the electromagnetic spectrum, from the low energy radio waves to the highest energy gamma rays. And you can see here is a radio image superposed on an optical image. Here is the optical galaxy. And you can see these huge blobs of radio emission, which can contain up to about 10 to the power of 60 ergs in energy generated by what we believe to be accretion of matter onto a compact object at the center. This is another example of a very famous radio galaxy. And optical galaxy is right over here. And total energy is about 10 to the power of 60 ergs. Radio luminosity, you can see, is of the order of 10 to the power of 45 ergs per second over here. Okay, I'll just mention this last class of active galactic nuclei because these are amongst the most luminous objects in the universe. Quasars, these appear star-like in normal sort of astronomical observations unless you have very high dynamic range. And the first such object was determined by accurately determining the radio position and finding that it was coincident with a star-like object. That itself was a surprise when it was first discovered, because stars are generally weak emitters. The sun is strong because it is very close by, and except for some very exotic stars, they're very weak emitters of radio emission. But when they took a spectrum of the star, unlike absorption lines, it had very prominent emission lines. And from the emission lines, it was established, it's a long story, but to cut it short, that it is indeed very far away from us at a distance, luminosity distance of 760 megaparsecs, which made it one of the very luminous objects. Today we have objects which are far, far more luminous. But when it was discovered, this was amongst the most luminous objects in the sky. As a star, it was a very ordinary star. But in terms of the total luminosity, it was amongst the brightest objects, or most luminous objects that we know. And again, here too, accretion onto a supermassive black hole is believed to be the source of energy. So I'll show you just one image to illustrate that what we are saying is probably okay. Our hypothesis, which we have derived from our very basic understanding of physics, is probably all right, by looking at one particular galaxy. active galaxy. Don't worry about the names right now. The basic picture is the same. This is a Seyfert galaxy. For those of you who are familiar, but don't worry too much about the kinds over here right now. Now, what we find over here, what has been done over here is that you can go deeper and deeper into the nuclear region of a galaxy to look for this kind of structures. But usually in the optical region of the spectrum, it is very difficult to do that because there's a lot of obscuration due to gas and dust in the galaxy. For example, the center of our own galaxy, it is difficult to see in the optical because of the medium between the stars consisting of gas and dust, which obscures it. But when you go to longer wavelengths, right, in the radio wavelength, you can go directly into the nuclear region. Obscuration is very minimal. Now, this is a galaxy from the central region of which if one took a spectrum, one could find that there was major emission from water vapor. But it had a very large velocity range. When one took a spectrum of it, frequency will translate into velocity, but you needed extremely high angular resolution. Like looking at a 5 rupees coin, if you had it in Lal Killa or at top of Qutub Minar and you are watching it from Ferguson College, you need to do similar or better than that to be able to look at the nuclear regions of galaxies. So you can imagine the kind of angular resolutions that one is talking about. And this is a relatively nearby galaxy. For more distant galaxies, it even becomes more challenging. So when you do that, you find that some of the major spots are coming towards you and the others are going away from you. There's one which is redshifted, the others which are blue shifted. Okay? And they all lie in a point as though they're forming a part of a disk. Detailed modeling shows that it is a warped kind of disk. And these are moving about the center just as the planets are moving around the sun, obeying Kepler's laws of planetary motion. If you see directly over here, you're going to see the green spots, which are very little very little velocities because they are orthogonal to line of sight, because what you measure are the radial velocities. And applying Kepler's laws of motion again, just as if you knew the distance, because you know the distance, you know the separation, so you know how far away it is. So just as for the sun, the velocity goes down as 1 upon square root of r. You'd find you're applying Kepler's laws and try to estimate what the mass of the central object is, and you get a supermassive black hole. So all I want to say is that observationally, I've just shown you one example of it, but there is a wide variety of evidence to show that this basic scenario, that gravity is a source of energy and gravity can explain a wide variety of phenomena. We started today with how birds use gravity, the energy that it gets to get at their food, but you can see that gravity plays a very important role right from the formation of stars to understanding the most energetic objects or the most energetic galaxies in our universe. Let me see, I should probably, yeah, I'm actually nearly at my time. So I'll probably skip these 2 last slides, okay? Or maybe I'll just skip these 2 last slides, or maybe I'll just mention it very briefly. Okay, I'll mention very briefly. Is it all right, Pranav?
Yes, sir, it is all right. You can take
Okay.
5 minutes.
I can take 5 minutes, okay. Yeah. Now I can do another simple thing, okay? Now, for example, all of us would have done drills in school, right? And if while doing drills, putting your hands up, left, right, whatever, if we did it all randomly, there would be a random number of hands which will be up or down. But the drill master usually beats a drum and all hands go up at the same time. So when I said these objects vary, okay, there would have to be some signal which will make different components in the disk or the vicinity of the black hole vary. So there has to be some coherence in the way all the different components vary together to give you a net variability. Now, if I take the Schwarzschild radius, now I know the last stable orbit is about 3 times the Schwarzschild radius, but this is just order of magnitude calculations. The minimum time scale of variability that I'll get will be Rg upon C, because over here the signals would travel at the velocity of light, and I can use Rg over here it depends on the mass of the object and then translate into solar mass. So what I can do over here is that depending on the mass of the object, I will get variability, okay, due to variability in the central region or the energy from closer to the black hole itself, varying the outer regions. If the mass is small, then it will be a smaller time scale. And if the mass is large, because the Schwarzschild radius is larger, it is going to be longer time scales. Okay. And from the shortest time scale, the variability that you observe, you could also get an estimate of the mass, right? Estimate of the mass. Here, actually, what are shown on the left side, this is a picture which I took from Longier's book on high energy astrophysics. It's a bit outdated, but this is just a straight, not a book, but the figures are a bit old. But just to illustrate the variability, here actually it's blown up. This is in seconds over here, and when you this is for a galactic X-ray binary, and these are for two extragalactic objects. Here, the variability time scale by the scale over here in seconds over here, you can see is much larger. Okay, and from the shortest time scale of variability, which you can infer from the observed light curves, you can go and estimate the mass. All right. You can also estimate a mass, as I said, without getting into too much details, is just by gravity again. Force of gravity and the velocity at which they are moving about. The velocity you will get from the line widths, but you need a measurement of the radius, which you can determine, but I will not get into that detail today. But once you do that, you can go and calculate what the mass of the object is. And this is a figure which shows that there is at least some similarity or rough relation between what you estimate from causality arguments about time, variability, and from the emission lines. And you can see these range from 10 to the power of 6 to 10 to the power of 10 solar masses or so. And they all radiate at a luminosity which is lower than the Eddington luminosity. So this is the forbidden region where the luminosity would overcome gravity, but that has not happened even for the most luminous objects. So I will close now with just a few closing remarks, that what we have seen today is applications of physics in understanding objects on a cosmic scale, but we've also seen that how gravity is used in a variety of situations, from birds getting into their food to different kinds of objects that is observable in the universe. Now, and what you also notice is that many of these discoveries which I talked about, the radio galaxies or the quasars or the most energetic objects in the universe, they were not theoretically predicted. They were not theoretically predicted. It's not that somebody sat down and did it. Of course, there are beautiful examples of where there have been theoretical predictions. But a lot of, for example, gravitational radiation, which Einstein predicted, also gravitational bending of light, the exact formalism based on the general theory of relativity, which was proven initially by Eddington, and today we see gravitationally lensed images of that. But a lot of observational astronomy, a lot of astronomy is also observationally driven. Today, the fantastic advances in cosmology or in our understanding of the universe, right from the discovery of radio galaxies and quasars, were actually driven by observations. Opening up of the radio window to observe the universe was observationally driven. And that has been possible due to technological advances. And technology actually has played a major role in significant advances in our understanding of the universe. So although from aspects of the philosophy of science, people talk about verification and falsification, or Popper's ideas or Thomas Kuhn's about there being revolutions in ideas because of inconsistencies which build up, fantastic advances take place often by serendipitous discoveries using technological advances. And that is an aspect which I would also like you to take home, because today even detection of gravitational waves, which was predicted 100 years ago, more than 100 years ago, has been possible due to the technology which is possible to measure such small shifts in an interferometer. And the whole window of radio astronomy got opened up by radar engineers not radar engineers, by Carl Jansky, who was investigating transatlantic communication with his antenna to identify sources of noise and identify a source of emission, the center of our own galaxy, which is due to synchrotron emission, which is due to ultra-relativistic particles moving in magnetic fields. Nobody predicted theoretically that synchrotron radiation, go and look at the center of the galaxy and you will find synchrotron radiation. It took many years and seminal work by Russian astrophysicists as well, Ginzburg, Starburst, others, to enable us to interpret the radiation as being due to highly relativistic electrons moving in magnetic fields. So today, I think I'll close with these closing remarks, and I'll be happy to take any questions. Thanks very much.
Thank you so much for this amazing talk, sir. If any participant has any question, then you can raise your hand or you can text the message in the chat box. Okay. Okay. So there is one question from Pranav, sir.
Yeah.
He is asking, when a pulsar with a binary companion accrete matter from it and spins up, we say that the pulse is recycled. Does the trajectory of this accreted matter, does the trajectory matters of this accreted matter? And because if the accretion happens in opposite direction of pulsar spin, the pulsar can spin down and its signal will fade out.
Yeah, no, I think Pranav, you made an interesting point. I had not touched upon pulsars today, but millisecond pulsars are ones which are being which are recycled pulsars, and where you can see that the period is actually spun up, and so the accretion process has to go in a direction which will actually have to spin up the pulsar. Right? Is that what you asked, or have I misunderstood your question?
Yes, sir. I guess that's what he was asking.
Okay.
So there is another question from Devin. Devin, would you like to ask that question directly to sir? Just raise your hand so that I can unmute you. Yeah, okay. Go ahead.
Yeah. Sir, how will you define gravity, and what is your opinion on what the gravity means? How the two objects attract or repel?
Okay, I mean, today we are governed. I mean, gravity has to be understood in the formalism of Einstein's theory of relativity, right? The general theory of relativity, and that forms the basis of our understanding of gravity. And actually, let me just sort of try and reframe your question.
So,
what you mean is, sorry, go ahead. You want to say something more?
Yeah. So he is asking, how will you define gravity, and what is your opinion about the cause of gravity?
Oh, gravity. I mean, the thing is that it's not my opinion. Gravity is due to the curvature of space-time, and Einstein's general theory of relativity actually defines our understanding of gravity today. And for example, in the vicinity of a massive object like a black hole, the space-time continuum is much more curved than in the case of further out, or in the case of less massive objects. So gravity today is understood entirely in the formalism of Einstein's theory of gravity. But on the large scale, for example, when I look at the motions of planets, for example, I can understand in terms of Newtonian formalism, in spite of sort of the challenges that it has in terms of action at a distance and all that, and the instantaneity of the force. But I can understand phenomena such as the motion of the planets, or even in the case of the major spots that I talked about in terms of applications of Kepler's laws. But when I look at regions of strong gravity in the vicinity of black holes, I'll have to look at it in terms of, understand it in terms of Einstein's formalism of the general theory of relativity.
Yogesh, you can ask your question. Hello? I guess there is some problem.
I think Vaishali also has her hand up.
Yes. Vaishali, you can unmute yourself and ask your question.
Hello, sir. Good morning, and thanks for the wonderful session.
Thank you.
I have heard in one talk that the primitive black holes are evaporated. Then my question is, how can a black hole evaporate? And is it possible that after some years or millions of years, the black hole which are exist today will evaporate?
Actually, I mean, I will touch on it very briefly because I think you have a talk later on evaporation of black holes and Hawking radiation. All right. Now, see, the evaporation of black holes, these are mechanical processes which occur near the surface of the black hole. Okay, and this was worked out by Hawking after, I believe, a visit to Russia with discussions with the Russian astrophysicists. He came back and worked it out, and he showed that black holes radiate. But the thing is that the only sort of significance of it is that it is only true for, I mean, in terms of observational consequences, it will only have for the smallest sort of black holes in terms of time scales. Okay. And also the other thing is the temperature, that it will not, the temperatures are low for it to have, observational consequences for observing these evaporation of these black holes. But theoretically, what Hawking has worked out in terms of Hawking radiation, that is definitely a possibility. Yeah. But watch out for a talk which you have on Hawking radiation. You'll learn much more about it. Yes. So I'll not say too much about it right now.
Yogesh, you can unmute yourself and ask your question.
So actually, my doubt is during the Penrose process, that is gaining energy from the spinning black hole. Does it stop the black hole spinning after a certain number of time, sir? Because when a matter falls in, it gains only energy and or mass. It doesn't gain any angular momentum. So does the angular momentum fades away over a certain period of time?
See, the thing is that there have been processes which have been talked about in terms of extracting energy from the black hole. There is a Stanford ionic process, and the thing is that it will take energy. It gets energy out of a spinning black hole, and once it gets energy out of a spinning black hole, I mean, the time scales would be extremely long. But in principle, yes, that the angular momentum will decrease because energy is being taken away from the spinning black hole. And ultimately, if all energy gets taken away, then it will be non-rotating black hole. But the time scales are, yeah, sorry.
So also does exist equilibrium, sir, in the center of the galaxy in black holes, because whenever black hole attracts mass, it gains some it will be powerful and attack more mass, sir. Also due to Hawking's variation, it loses some of its mass and loses its gravitational force power, sir. So does there exist equilibrium, sir, on gaining and losing its power?
Actually, the amount of Hawking radiation is small, all right? And the thing is that today we know that, for example, the example which I showed you about 10 to the power of 7 solar mass black hole in the center of NGC 4258, which we have been able to determine from Kepler's motion, from the motion of the major spots. Now, if you look at the question that how do I get a 10 to the power of 8 solar mass black hole? Right? Now, that clearly has to do with the evolution of the galaxy and the evolution of the galaxy itself. Because what we find today, I didn't touch upon that at all, is that for example, if you take a galaxy I'll just take the two broad classes of galaxies. One are the spiral galaxies like our own, which have a bulge in the center, which is largely sort of spherical. And there are elliptical galaxies, which look elliptical and have either usually no spiral arm, sometimes the vestiges of a spiral arm. The mass of the black hole that we see is intimately related to the properties of the bulge in terms of its mass and velocity dispersion. Okay, so the way the black holes actually grow, black holes grow, is related to the way the bulges develop as well. So clearly the black holes have grown over time, over cosmic time, to be of the order of 10 to the power of 9, 10 solar masses or so. And this is one of the very frontier areas of physics to try to understand the growth of black holes along with the evolution of galaxies. And in terms of the Hawking radiation for these massive galaxies, that will not be a very significant effect on the timescales that, particularly on the timescales that we are talking about. So growth of black holes, the amount of masses that we see, has to do with the episodes of actually accretion of matter onto it, coalescence of black holes themselves, which may give rise to gravity waves. So that is an interesting and a frontier area.
So I think we can safely conclude that galaxies eventually fell out into the black hole.
No, galaxies may not fall into the black hole, because you can see, for example, our galaxy, if you look at it, we have a 10 to the power of 6 solar mass black hole sitting at the center. It is, and by looking at the motions of stars within the vicinity, for which the Nobel Prizes were given to Andrea Ghez and Reinhardt. Okay, so Genzel. So you can see that stars are moving about due to the motion of the galaxy, but it's only 10 to the power of 6 solar masses, and we have 10 to the power of 11, 12 stars making up our galaxy, extending to tens of kiloparsecs. And then this whole galaxy is only a small fraction of what we actually see, because this whole galaxy is embedded in a halo of dark matter. Okay, so the galaxy is not going to collapse into a black hole, but a black hole can grow with time due to coalescence, accretion of matter in terms of its mass. But it's unlikely that a galaxy will fall into a black hole, because what we see is, as we know, that baryonic matter, which we see, is just 4% that makes up the universe. About 25% is dark matter, when you close to that. And the dark matter, and all these galaxies are embedded in dark matter halos, which make up a major component, which we have inferred again from the effects of gravity by looking at the motions of gas clouds and stars. So it will not fall into the black hole, right?
So we have a question on YouTube from Kiran Wani. He is asking, how do we confirm the radiation which we are observing is thermal or non-thermal in nature, or we have to only rely on the empirical calculations as you described in the in your PPT?
Okay, that's actually a very good question. Okay, it's a very pointed and good question. Let me just elaborate on that a little bit. Okay, suppose, for example, I saw a blob of radio emission in the sky. All right, how do I establish what is the energy process which is responsible for the emission that I see? I mentioned about the radio lobes being due to synchrotron emission. How do I know it's synchrotron emission? What are the defining characteristics? And at radio frequencies, as far as the continuum emission is concerned, there are two dominant processes which take place. One is what is called free emission or thermal Bremsstrahlung emission, which is when matter is ionized and the charged particles are moving about in a Coulombic force, and these accelerated charged particles give off radiation. All right. Now, and the other one is what is called synchrotron radiation, or earlier it used to be called magneto-Bremsstrahlung, where highly energetic particles are moving in magnetic fields. Right. Now, as far as your question is, how do I distinguish between the two? So the first thing you notice is that one of them involves a magnetic field, okay? Involves a magnetic field. And as long as there is a uniform component to the magnetic field, it's not completely tangled up, that you're going to see a degree of polarization in the radiation due to synchrotron radiation. Whereas from thermal free emission, which is, for example, you heat a gas to very high temperatures. For example, Orion is a constellation which is up in the night sky now, and you know about the Orion Nebula. The Orion Nebula also emits continuum emission at radio frequencies. And that is due to free thermal Bremsstrahlung emission, which is acceleration of charged particles in a Coulombic field, and that has no preferred direction. So one distinguishing characteristic is the polarization. So free thermal Bremsstrahlung will not be polarized, whereas synchrotron or magneto-Bremsstrahlung emission will be polarized. In the case of a single electron, or in the case of a reasonably uniform magnetic field, the degree of polarization could be as high as about 70% or so. All right. So you can see that the degrees of polarization is one very clear distinguishing factor to distinguish between free emission and magneto-Bremsstrahlung or synchrotron emission. The other very important difference is the spectrum of the source. That is, if you measure the intensity as a function of frequency over a large range for both these two kinds of emission, there are very striking differences in the spectrum of emission. For example, in the free emission, due to absorption processes, it can turn over at low frequencies, but at higher frequencies where it is optically thin, it is reasonably flat. With a spectral index, if I define it as flux density proportional to nu to the power of minus alpha, where alpha is the spectral index, and if you plot it on a log-log plot, then alpha would be the slope. In the case of free emission, it will be about 0.1. Whereas in the case of synchrotron emission, it is a power law with a much larger slope. Here also it can turn over at low frequencies of absorption or steepen at high frequencies due to radiative losses. But it has a power law with a slope of about roughly about 0.8 to about 1.2. There could be some flatter, some steeper as for an optically thin source. So both spectra as well as polarization are the distinguishing characteristics. And in the case of the non-thermal sources, the steep spectra arise because of a non-thermal distribution of the electron energies itself, which are radiating, with the higher energy electrons radiating at higher energies, higher frequencies, and the lower energy electrons radiating at lower frequencies in a given magnetic field, right?
So if you have a time, then we can take one last question.
Sure.
That's okay. Yeah. So Vinayak, you can unmute yourself and ask your question.
Sir, does any effect of luminosity of galaxy due to death and the birth of stars?
Due to the death and birth of the star. Okay. Now, for example, if I were to look at the luminosity of a galaxy, right? Now, I mentioned that when there are 10 to the power of 11, 12 stars in a galaxy, that if it is passively evolving, like our own galaxy or the Andromeda Nebulae or similar galaxies, that one supernova going off is not going to affect significantly the whole luminosity of the galaxy. But on the other hand, if I have galaxies like the Starburst galaxy, okay, where, I mean, obviously not going to vary on very small time scales, but you can see that the luminosity of that galaxy would be affected quite significantly by the starburst that is going on. Okay, because when there is a very high star formation rate in a galaxy, then stars form when they form with many more low mass stars but less high mass stars. But what you have over here is that when there's a starburst, there would be a lot of high mass stars which are forming, and these high mass stars, because the more massive a star is, the more luminous it is, and also also it emits more of these higher energy photons. Okay, and these photons are going to heat up the dust in its vicinity. And the dust is going to radiate at the infrared wavelengths. So many of these star-forming galaxies, you will find them extremely luminous in the infrared. For example, one came to know about the existence or the ubiquitousness of these class of galaxies when the initial astronomy satellite, the infrared astronomy satellite IRIS went up, where just the infrared luminosity of the galaxy could be about 10 to the power of 12 solar masses, or 10 to the power of 12 times the luminosity of the sun, just in one waveband. And these are called ultraluminous infrared galaxies. They are also called hyperluminous infrared galaxies. So the luminosity of a star, of a galaxy in its history can be governed by the star formation that is going on, the current star formation rate. By current, I mean at the time at which we see it, it will be obviously governed by the look back time to the galaxy. Can be governed by the star formation rate, but an individual supernova going off may not affect the entire luminosity of a galaxy. Although we now know that know the phenomena of gamma ray bursts. The gamma ray bursts can sometimes outshine or can be a major significant component in affecting the luminosity of a galaxy. But a simple supernovae is not going to affect the entire luminosity, but these gamma ray bursts, which also emit out jets, which could be beamed, and because it is beamed, the luminosity is further enhanced. They can play a significant role. All right.
Thank you so much, sir, for this amazing talk, and it was a really great talk, and we got to learn various new things. Maybe after this pandemic situation is over, you can visit Ferguson College and we can host a talk here maybe in amphitheater if it is open. We would really love that. And
Thank you very much, Prabhanjan, for your kind comments. And thanks very much to all of you, and Ravade also and Pranav Lemay for the kind invitation, and the Astro Club of Ferguson College. I also noticed Professor Wag coming up very briefly. So it's been a long time since I met him, and it will be a pleasure to visit Ferguson College once the pandemic gets over. So best wishes to all of you for the rest of the session today. Thank you very much.
Thank you, sir.
All right, so a small reminder to everyone. The next lecture will be given by Dr. Sudha Rajmani, the Associate Professor and Deputy Chair of Biology at IISER Pune. The lecture will be on the topic of the astrobiological narrative of life's origin, and it will start from 3 p.m. So hope to see you all then. Thank you.
Rishi, will the same link work if I want to listen to the talk?
Yes, sir. The same link.
Okay, thanks very much. Thanks.
Thank you, sir.
Thank you very much. Thanks.